Okay, thank you very much, everybody. Okay, now before we begin, I'd like to say something first to everybody. Now, this training and workshop we are doing is in due to the preparation that we are going to do some assessment being done by the IAEA requested by the Indonesian government. So we are on the process of being assessed, and hopefully in collaboration also with Bapeten, we have written letters to Bapeten on this issue. So we hope that people who participate in this training workshop can also be participating in the assessment with IAEA. So that is the purpose why we are having this training and workshop in preparation for the IAEA assessment that hopefully we're going to start somewhere early August, as soon as the requesting letter from the Indonesian government is sent to IAEA. So with that, I don't like to extend. So with that, I'd like to give the floor to Professor Kun Chen. Please, Kun, the floor is yours.
Thank you very much, Bob. So let me try to share the slides. Okay, if this is the one I want to share. And let's do this. Can everybody see my slides?
Yes, yes.
Okay, that's great. Okay, so again, I'd like to thank Bob again for giving me this opportunity to participate in this workshop and share with you my experience and the knowledge about the molten salt reactors. As you can see, we have a, oh, just a second, how do I move this slides? Okay. So at this moment, we're thinking about a 6-session workshop, and today is the first one. We're gonna do an introduction, which we have just done, and then I'm gonna spend some time discussing the history and current status of MSRs, which would include the early development back in the 60s and the recent work that has been done by several countries in the world. I'm also going to introduce a little bit about my past work with SINAP, Moltex, and the licensing experience in China and Canada. The second one, which is next week, I'm thinking about we can introduce the general information about Thorcon 500, which is the main topic of this training series. And then we're gonna touch base on each of the technical areas, such as neutronics, some hydraulics in the third week, and then we go into the operation and balance of the plant, and then we go to off-gas instrumentation and control and radiation protection. The last one, we're going to talk about the safety assessment, typical MSR DBAs, and also the precision tester platform. This is just a tentative schedule. We like to hear your feedback. If you think anything you're interested, you want us to present, we'll be happy to add those topics into the schedule. And also the workshop is organized that we start the presentation maybe in the first hour, and then we leave plenty of time for questions and comments and discussions. And those parts are the part I'm very much looking forward to. I really like to hear from you, your experience and your knowledge on the molten salt, and also the nuclear power development in Indonesia in general. So again, very excited about this opportunity. So I think to Okay, just give me a second. I don't think every time okay. Okay, so the first week is really about introduction and history and current status of MSR. And Bob asked me to introduce myself, so I made a simple slide. I can go from my early career to the recent responsibilities. And I attended college in China, and my major was in applied physics from the University of Science and Technology of China. And after I got my bachelor degree, I went to the United States for advanced degree. I attended University of Notre Dame and also the Indiana University. I got my PhD in nuclear physics and scientific computing in 2006. And then I joined the Argonne National Laboratory as a nuclear engineer. I was there working on criticality safety and shielding calculation and several other topics, which is a very exciting experience for me. And then after that, I moved back to China, to Shanghai, to join SINAP, which is called Shanghai Institute of Applied Physics. The reason I joined this institute was that back in 2010, 2011, there was a major molten salt development project in that institute. That was probably the only major molten salt reactor development activity in the world at that time. And still that up to this day, that's only molten salt reactor that's under construction. So I was there to lead the safety analysis and licensing and part of the engineering design and research development. I served as the director of the reactor system and engineering division. I was also the deputy chief nuclear engineer for safety. And so that was in the year between 2011 and 2018. And at that time, I get to know Bob and other folks from Thorcon. And also I had the honor to host a team from Indonesia, I think back in 2017 or 2018, and also get to know Professor Waris during that time and was going to visit Indonesia. But then I left SINAP. I moved to Canada, which I'm currently living in Canada. So I moved to Canada because I joined the Moltex, Moltex Energy Canada, which is also a molten salt developer originally from UK. And they had a technology called a stable salt reactor, which is a fast spectrum molten salt reactor. I served as a VP for licensing and regulatory affairs. And again, I was leading the pre-licensing activities in Canada, which it's called a vendor design review. And the work is for the vendor to submit their design to the regulator. In this case, it's the CNSC, the Canadian Nuclear Safety Commission. And once the vendor submit their design, the CNSC will review it and will identify gaps and will require or recommend the vendor to fill those gaps. So that work has been going on for 2 years. And by May this year, the work has done, and you can find the conclusion of that work from the CNS's website. And then after I done my work in Moltex, I left Moltex and joined Thorcon, which I become a team member with Bob. And so I'm currently serving as the Chief Nuclear Officer for Thorcon International. So I'm leading the effort to go through a IAEA technical safety review, which, as Bob said, is going to start August this year. And I'm also doing several other things to help Thorcon to develop the power plant in Indonesia and around the world. So this is basically a short introduction of my career. I'm very much looking forward to work with everybody who are interested in molten salt and nuclear and to make this happen. So regarding today's presentation, I'm going to start with a short introduction on what is MSR, because as you can see, there's so many types of MSRs around the world. And when you talk about MSR, what exactly that is. And I'm also going to introduce the history of MSR in the United States and around the world. I'm going to highlight the early development of MSR in Oak Ridge, because that was everything started. But a lot of people may not be aware that there was a lot of MSR development around the world back in the 60s and 70s. And those work has been published, and you can actually find out those interesting early work. And then I'm gonna explain or try to explain why MSR stopped in the United States, because that question has been asked many times. And also I'm going to introduce a recent work that was done by the IAEA on the taxonomy of the MSRs to try to explain to you how can we categorize all type of MSRs and what are their features and what are their pros and cons. So I also feel it would be beneficial if I introduce a little bit about the MSR development in China, because there was a major effort going on in China, and also the people in SINAP, they started from scratch. So I think for anyone who want to establish MSR capabilities, there might be something interesting to them to take a look at experience the Chinese had on establishing those capabilities over the years. And the last but not the least item is a comparison or in a short introduction on the Chinese and the Canadian regulatory processes. The Chinese test reactor, the molten salt test reactor, has been licensed in China. So how they do that might be interesting. And also the CNSC in Canada, they're reviewing several molten salt designs and doing the pre-licensing work. Because I personally led the effort of those work, so I like to share my experience with you, and hopefully that will be interesting to you as well. Okay, so let's move on to the first item. So what is MSR? There's a lot of definitions, but I'm trying to use the one that was given by the IAEA. There is an ongoing effort to collectively summarize all the MSR effort around the world at this time. the IEA is developing a tech doc to summarize that work. It has been going on for several years, and I am one of the authors of that tech doc. And unfortunately, it's still a draft. We were hoping to publish that 2 years ago, but as you can imagine, the work involves so many countries and so many authors. We had a lot of discussion on how to make this tech doc perfect. We may not be able to achieve that, but hopefully we will be able to publish that tech doc this year. So the information we collected will be shared with everybody. And according to the IEA, the definition is that the molten salt reactors are a broad and diverse category of reactors in which a molten salt plays one or more significant functions in the core, such as fuel, chemical form, a liquid fuel carrier, coolant, or moderator. So basically, if the reactor is using molten salt either for fuel or for coolant or for moderator, it can be considered as one of the MSRs. So as you can see, by this definition, we will include a lot of reactor design into the MSR family, which I will do a taxonomy in the latest slides to give you a more clear picture on the MSRs. And it is necessary to recognize that MSR is one of the 6 generation 4 nuclear reactors recognized by the international community, which has the potential to use fuel more efficiently, reduce waste production, and be economically competitive and meet stringent standards of safety and proliferation resistance. If you have any questions, please, you can leave your comments or raise your hand. We can have those discussions after the presentation. Okay, so the history of MSR started in the United States. There was an aircraft nuclear program back in the 1940s and the 50s, supported by the US military. And as you know, the Navy, the US Navy has chosen the PWR for the power and to power their submarines and carriers. But at that time, the US Air Force actually was thinking about using molten salt to power their airplane. And the idea is to let the airplane flow in the air for a very long time, so they can be used to defend against potential Soviet Union invasion. So the first MSR in the world, which is called ARE, was built and operated in Oak Ridge National Laboratory in 1954. So that was very, very long time ago. And the ARE actually operated for only 100 hours. So by any standard, it won't be considered as a long-term operation. But it was the first MSR, and it gives a lot of experience to the later developments. Unfortunately, a lot of those information has been recorded and made available to the public. So that ARE, the success of the ARE actually led to the most famous MSR in the world, which is MSRE, the molten salt reactor experiment. That MSRE achieved initial criticality in 1964. And here is the enhanced picture of everything actually inside the containment. As you can see, there's just let me try to find my laser. Okay. As you can see, here's the reactor vessel, the pump, heat exchanger, and everything else. And the MSRE operated from 1965 to 1969, which is 4 years, and it can be considered as a long-term operation. And most of the information we have at this time regarding MSR was from the MSRE, and almost all of the design you have seen nowadays are more or less connected to the MSRE. The MSRE has used uranium-235, 233, and plutonium-239 as its fuel. It was operated at a full power, close to 8 megawatts thermal. The MSRE was actually part of the thorium-uranium fuel cycle development. So when they developed the MSRE, they are thinking about using thorium. And the reason they put the uranium-233 into the MSRE was to prepare for the future thorium fuel. So the MSRE is very famous, but at the same time, and shortly after that, there's a lot of efforts going on in other countries to develop MSR. And I'm going to do a short introduction on those in alphabetical order. So China actually started MSR development back in early 1970s in SINAP. The purpose was to develop a reactor that can use thorium fuel, because it was perceived that China has much more thorium reserve compared to uranium. And actually a zero power cold state MSR was actually achieved its initial criticality in the same year. And it only took 3 months for the test bed to be built and reach the criticality. And in France, the AMSTER concept was proposed by EDF, and another concept called TMSR was proposed by CNRS in the late 1990s. I have to point it out that I'm listing the time here that for a major concept or major project was initiated. If you consider the early R&D effort, you could find an even early paper that was published. So in Germany, there was another concept called MOSEL was proposed in the 1960s. In Japan, a concept called Fuji was proposed for the first time in the late 1970s. Netherlands, they have their development into Delft back in 1970s. In Russia and former Soviet Union, also in Switzerland, a concept called SOFT was proposed by PSI in the late 1970s. Of course, United Kingdom also had their MSR development back in 1960s. So as you can see, during the same time the MSRE was successful, there's a lot of parallel efforts that's going on in other countries. So with all these efforts, why MSR seems to stop after 1970s? So as we all know, the MSRE was quite successful because it operated for 4 years and achieved its original goals. So the natural step for the development is to build a larger, high-power demonstration reactor to further perfect the technology and to enable the commercialization of this technology. So after the MSRE in 1972, the US Atomic Energy Commission, the AEC, which at that time is the sole government agency that managed all the nuclear activities in the US. And it conducted an evaluation to determine if a large demonstration plant should be built in the United States. And the conclusion of the evaluation was documented in the report called WASH 1222. And that report was made available online. You can just Google WASH 1222. You can find the AEC's conclusion on MSRE and their recommendation on the next steps. And the WASH 1222 report indicated that MSR was not high enough on the US government's energy development priority ranking. So at that time, the US government ranked sodium fast reactor higher than all the other technologies. And the government recognized that they don't have all the necessary resources, means money, to support the parallel development of all the technologies. So they choose SFR, the sodium fast reactor, over other technologies. And they dropped not only MSR, but also a high temperature gas cooled reactor, and also several other technologies. And the WASH 1222 also identified several technical issues that require further studies. And the number one issue is the neutron embrittlement of nickel-based alloy at high temperatures. As you may know, that MSRE is using a nickel-based alloy. Nowadays, we call it HETEROGENEous. There's several other versions of that. And it turns out that if the neutron fluence was too high, or the vessel was put into service for too long, there will be embrittlement effect of nickel-based alloy. And the second one is the radiation damage and the dimensional change to graphite at high fast neutron fluences. And the graphite has a special characteristic that it will expand with the neutron irradiation, and then will shrink after you reach certain dPAs. And the third one is the liquid-liquid chemical extraction process. If fuel processing is required. At that time, the Oak Ridge was thinking about doing reprocessing of the fuel. So a chemical process needs to be developed. The fourth one is the tritium permeation of alloy. And because the MSRE is using lithium salt, which will generate a relatively large amount of tritium, and at high temperature, the tritium can penetrate alloy. So this issue needs to be resolved. And the fifth one is development of large components. The MSRE is using a special nickel-based alloy. It's relatively small because it only have 8 megawatts. If you want a larger demonstration power plant, you will need a larger nickel-based alloy components, which not available at that time. And also the understanding of fission products, which really about the release of cesium and iodine and other important elements. And also remote inspection and maintenance. If you want this power plants to continue operate for 30, 40 years, you would definitely need to do some inspection and maintenance, which you have to develop a robotic method to do that work. So because of this fundings from the AEC, after the evaluation, the US MSR program was refocused to resolve the technical issue identified in this report. So the next 10 years after the 1970, all the effort was actually on resolving the technical issues I just mentioned in the previous slide. By the end of the 1970s, the technical issues were largely resolved. So you would think by that time, the US will be ready to develop a large demonstration MSR, but the opportunity has gone. The MSR never became sufficiently highly important to obtain the required resources for the next phase of the development in the US until recently. And as you can imagine, by early 80s, there are several nuclear accidents happened, and the public opinion in the US has changed. So the MSR never get the adequate resource to be developed into its commercial use. You will hear a lot of arguments on why US stopped, but I'm trying to give you an official answer to that, and everything can actually be found in that Watch 1222 report. It's really about the priority of the nation on which direction it wants to go. It's not a simply right or wrong, but with limited resource, you have to focus your resource to the technology that you think you have it has the highest priority. It doesn't necessarily have things to do with the technology maturity or economics. It's a very complicated issue. But I'm very open to have this discussion with you to explore why the US stopped and why it actually revived recently in the US. Okay, so the next topic is about the current status of MSR in the world. If you look at the history, MSR was a very hot topic back in the 60s and 70s, and it goes down in 80s and 90s and even early 21st century. But somehow it got revived in the past 10 years. A lot of efforts, a lot of government efforts, a lot of private sector efforts emerged again in the past 10 years. There are several reasons for that. The climate change and the low carbon emission is definitely one of the reasons. So now there's so many MSR's concepts around the world. To be honest, if I'm a person new to MSR, I will be confused. And because there are so many choices for the MSR. For the few, you can have uranium, you can have plutonium, you can have thorium. And neutron spectrum, you can have thermal MSR, you can have fast spectrum MSR. And you can have a burner, you can have a breeder, and also you can have a converter. And for the storage, the most commonly used storage are fluoride and chloride. For each of the type, you can have all kinds of storage. And also I have seen other type of sorts. And the core, you can have single fluid, you can have two fluids, and some design have no fluid. Site, you have land-based, and you can have non-land-based, and within non-land-based, you can have floating, and you can have non-floating. So all kinds of choices. And in order to help people to understand the different type of MSR, the IEA is making an effort to do a taxonomy of all the MSR concepts that's available at this time. So the IES approach is very classical. It's doing a typical taxonomy method. Within the MSR, it has a different classes, and within each class, they also have families, and under families, they have types, and the types, they have all the individual designs. So according to the IEA, there's 4 major MSR classes. Now, the first one is the chloride-based MSR. So any MSR that use chloride will be put into this class 1. Number 2 is the homogeneous MSRs, which you have a homogeneous core. And class 3 is heterogeneous. In that you have heterogeneous core. And of course, there's always some concept that cannot be put into each of these classes. So you have the class 4 other MSRs. So under each of the class, there's at least 2 families. So you have a fluoride salt-cooled MSR and the chloride moderated MSR. I will have several slides to give you to give you examples, so you have a more clear picture on what exactly I'm talking about. And then you have homogeneous fluoride fast MSRs. You have a homogeneous chloride fast MSRs. And then you have a non-chloride moderated MSRs. You have heterogeneous chloride fast MSRs. So let me go to the example so you know what I'm talking about. Okay, the class 1, family 1, type 1.1 is the salt-cooled reactor with pebble bed fuel. So the example I'm giving here is the University of California, Berkeley's design, which use pebble bed fuel as a fuel, but just use the molten salt as coolant. And the other type is salt-cooled reactors with fixed fuel, which is the Oak Ridge concept. It's very similar to the Berkeley concept, but the only difference is the fuel. It's not a pebble bed fuel, but it's a fixed slab fuel. But they all use molten salt as coolant, but not as a fuel. And second family, we have a single fluid thorium uranium breeder and 2 fluid thorium uranium breeder. In these 2 types, they all use graphite as a moderator, so it's a thermal reactor, but they're breeders. So you have an Oak Ridge single fluid MSBR concept, and then you have Oak Ridge 2 fluid MSBR concept. So I'm trying to use the example that has a published result, so you can find their information online. I'm leaving this references here. There's other examples you can find, but if they don't publish, you don't have a lot of information on that. So the next type is actually, in my opinion, is the most important type of all these different MSRs. It's class 1, family 2, type 2.3, which were called uranium converters and other concepts. So it's important because the Oak Ridge MSRE, the only MSR that operated for a long time, belongs to this type. Also, the Thorcon 500, again, is the same type. And also the Japanese Fuji, and also the SINAP test reactor. So all these four concepts actually belongs to the single one type. So these concepts are most closely related compared to other types. And then we have also other types. We have what we call homogeneous fluoride fast MSRs. We have fluoride fast thorium uranium breeder, which is the French concept. And then we have a plutonium fueled fluoride fast reactor. It's a waste burner type of reactor. A typical example is the Russian MSR concept. And then we have this homogeneous chloride fast MSR. The example is the Swiss soft concept. In the class 3, it's a heterogeneous concept. We have both solid moderator heterogeneous reactor and liquid moderator heterogeneous reactor. And the Oak Ridge ARE back in the 50s was using beryllium as moderator. So it falls into the concept of solid moderator heterogeneous reactor. And recently, there's two concepts from Denmark. One is from Copenhagen Atomics, and the other one is from Seaborg. They're both based in Copenhagen, and they belong to the liquid moderator heterogeneous reactor. As the one you see here, the Copenhagen Atomics concept is really in the box, and we cannot see it, but we can see Seaborg, which have the fixed field channels, which serve as very similar to field pins. So we call the heterogeneous reactor. And the last one is the heterogeneous chloride fast MSRs, which we have heterogeneous salt-cooled fast reactors. A typical example is the Moltex stable salt reactor. So the fuel is actually, the molten salt fuel is not flowing. It's being sealed in fuel pins. So it works like the PWRs. And that's why it's called heterogeneous reactor. And some designs actually not using molten salt as a coolant. It use lead, liquid lead as coolant. So it's called a heterogeneous lead cooled fast reactor, which we have a German DFR concept here. And there's other different MSRs concept that cannot be put into the previous categories. So you have all kinds of interesting concepts. So I'm not going into the details of that. I think it's worthwhile to do a comparison of the MSRs. As I mentioned, the Oak Ridge MSRE, the SINAP TMSR test reactor, and Thorcon, they're belonging to a single type, which closely related to one another. So I think it's worthwhile to compare those three to give you an idea of why they're, what are their differences, what are the common features. So if you look at these three designs, they have different power level. The ORNL MSRE, the actual thermal power was 7.34, and the SINAP one was supposed to be running at 2 megawatt thermal. So both of them are in the low power range, and the Thorcon 500 is a commercial reactor. So each Thorcon power module will have 250 megawatt electric, and 2 of them will give you 500 megawatt electric. In terms of fuel, the MSRE has used the uranium-235, 233, and plutonium-239. The SINAP one is going to use the uranium-235. They don't have uranium-233, but they're going to use thorium-233 as sample, which means the thorium fuel will not be mixed with the fuel salt, but rather it will be put into the a channel to be irradiated as a sample. While the Thorcon 500 use both uranium-235 and thorium-232. And as for the fuel salt, the ORNL is using lithium fluoride, beryllium fluoride, zirconium fluoride. And the SINAP one has exactly the same fuel salt composition. The difference on the Thorcon is it replaced lithium fluoride with sodium fluoride. The reason is that the lithium fluoride needs to be enriched, the lithium-7 needs to be enriched, and even after the enrichment, there's still going to be a lot of tritium generated by neutron irradiation. So by switching to sodium, first of all, it will significantly reduce the cost of the salt, because at this time, there's no industrial capabilities to enrich lithium-7. And also, it will help to significantly reduce the production of tritium. But the catch of using sodium fluoride is that it has a less effective moderation compared to lithium. So you will have to suffer a little bit neutronics performance, but you will benefit from getting this cheap sodium source. So you reduce your cost and also reduce your release of tritium. And all the concepts I'm mentioning here are using graphite as a moderator. And the ORNL MSRE is using nickel-based alloy, and SINAP again is using nickel-based alloy. And while Thorcon is using stainless steel. The reason is that, first of all, nickel-based alloy is expensive alloy. It's hard to get and hard to manufacture. If you remember, one of the WASH 1222 report identified that making larger nickel-based alloy components, it's a challenge for commercializing MSR, but the industry has no difficulty in making large stainless steel components. Another reason is that the nickel-based alloy has this neutron embrittlement issue. That issue can be mitigated by developing new alloy, but stainless steel in general have a better performance resistance to the neutron irradiation. Of course, there's always the catch comes with the benefit. For stainless steel, the chemistry control of the salt need to be maintained to mitigate the corrosion. For shutdown, they all use the shutdown rods. So there's no difference there. The passive heat removal, so the MSRE is actually use a drink tank. So when the fuel temperature is too high, the salt will be drained to the tank, and the tank will be cooled by water tubes. For the SINAP one, they don't use the drink tank. They use a cold war technology, which is actually used by the high temperature gas cool reactor people. So it's a mature technology, and the SINAP people just borrow that technology. For Thorcon use both drink tank and cold war. So the salt will be drained as MSRE to the drink tank, and the drink tank will be cooled by cold war. So this just gives you a general picture on the comparison of Oak Ridge MSRE, SINAP TMSR, and Thorcon 500. Okay, so since we're mentioning the SINAP TMSR, I like to use several slides to give you a short introduction on what's going on in China in terms of MSR development. And so the MSR project started in China from 2011. The idea to have this major development, which is kind of major because the total investment is definitely above 500 million US dollars. That was a major effort by the standard of money spent. So the reason the government was willing to invest because the MSR has the potential to use thorium resources in China. The Chinese government was concerned about the supply of uranium. As you may know, that China currently has many PWRs, and it's on track to build and operate 100 PWRs. And the majority of the uranium are from either Australia and Kazakhstan. So the government would like to have some domestic fuel supply. So they're looking at thorium, and MSR was considered to be one of the top candidates for using thorium. And also they wanted to explore the nuclear heat applications, which has been talking within the nuclear industry for over 20 years, although it hasn't been commercialized. Okay, so I want to share this slide with you because I think it makes sense for us to take a look at how SINAP was getting their capabilities. Even though I mentioned that China SINAP actually did some work back in the 70s, but as you can imagine, if you don't keep doing it, you will lose your capability. People back in the 70s, they have retired, and the facilities they used back in the 70s has been decommissioned. So in 2011, when SINAP started MSR development, there was nothing. So basically no people, no equipment. So the first thing they did was to establish capabilities. There's basically two types of capabilities. For analysis, the softwares are generally available, you can buy them, but the laboratory facilities, it takes time to establish those. So there's two major type of equipment or facilities you want to build if you try to develop molten salt reactor technology. The first one is the boxes for the molten salt chemistry study. And the second one is the molten salt loops for thermal hydraulics and operational experience. So SINAP at that time spent most of the time on instrument, glove box, and history. So here is just a very simple example. They built a large glove box. There's a multiple equipment like this in the institute. So it allowed them to do the salt chemistry, corrosion, and material studies. And then they got the molten salt loops, which you can actually start it with water loop and oil loop. And this picture showing here is not a molten salt loop, it's an oil loop. It gives you the opportunity to study the thermal hydraulics. And then once you gain experience and you can move on to the molten salt loop, as you see here, and the molten salt loops are more expensive. They're difficult to operate. For example, in this loop, melting the salt will take you a week, and then let the salt cool down will take you another week. So imagine this: if you try to replace a instrument or component in the loop, you will at least have to wait for 2 weeks, and then plus the time you have to do the maintenance. So the molten salt loop will be difficult to operate and takes more time. And you want to try to do as much as experiments on the oil and water loop. And once you once you get experience, you use molten salt loop. So those are the basic or fundamental R&D capabilities. And once you pass that stage and you want to move on to the industry and you want to say which components industry can make for you to build the MSR. And of course, there's three major type of material component. First one is the alloy. You want that for the structure material. And there's a salt. You want it for the fuel and coolant. And also the graphite, and you use it for moderator. So several suppliers were engaged. They're making this alloy, the graphite and salt for SINAP. So SINAP's not doing this by themselves. And so I want to show you one picture here, which is on the top right. As you can see, it's a centrifuge. So this one is the laboratory scale of demonstration of the enrichment of lithium-7. This was quite successful in the lab, but it was not a very successful in the larger scale. So up to this point, the large quantity, the large scale enrichment of lithium-7 hadn't been achieved in SINAP or by any of its suppliers. The lithium-7 salt the SINAP is currently using for the test reactor was actually bought from Russia, and they use a mercury technology which has been banned in many of the in many countries around the world. So lithium-7 remains to be a barrier for large deployment of MSRs. So that's also one of the major reasons that Thorcon switched to sodium. So with all these capabilities, R&D capabilities and industrial capability established, the next step is to put everything together. And so what SINAP did was to build a pre-fission tester platform, which they call TMSR-SF0. So the idea is to design and build a facility which is exactly the same as the reactor you want to build, but instead of using nuclear fuel as the heat source, they use the electric heaters. So as you can see on the left is the design of the facility. On the right is the actual facility that was completed in 2020. And the benefit of this, the first of all, you can do experiments on it. And the second, I think even more important, is that you gain experience on both making this components and operate this facility. So for the first reactor, you will definitely meet some challenges on even making those components in the workshop by the suppliers. And going through this will get the suppliers ready for making those components for you. And when you install it or you test it, you will find other issues, and it's much easier to fix those issues in the non-fission test platform compared to the nuclear power plant itself. So that was an excellent idea. If you're looking back, without this, the project might get further delayed because of those unforeseen issues. So with the pre-fission test platform done, SINAP is actually moving on to the test reactor itself, which is called TMSR LF1. So I'm not going to go into the details, but the pictures shown here is the vessel. The reactor vessel has been manufactured and shipped to the site. And what they're doing here is try to install the vessel. So by this time, all the major components, like the vessels, the pumps, the heat exchangers, they were all manufactured and they were all shipped to the site. And the construction license was granted in 2020. So I left SINAP in 2018, the end of 2018. So I was leading the application for site license and also the application for construction license. So by the time I left the institute, we have completed the PSAR and we have completed the application for construction license. So now after a year and a half, the license was granted by the regulator. And at this moment, they expected to reach the initial criticality next year. And the plan was actually originally to be this year, but due to the pandemic and the other issues, it was delayed for 1 year. So we're talking about moving the component to site. So where is the site? Here's a picture here. SINAP is in Shanghai, and the reactor site is actually much west to the Gobi Desert. The site is in a city called Wei. The site permit was issued in 2019 when I was still with SINAP. And as you can see, the site is a very dry and cold site. So the annual precipitation is only 128 millimeter, and the annual average temperature is 8 degrees. And the picture on the right is the site. Then after a few years, buildings were constructed, and right now they're doing the installation and of the major components. Okay, so my last few slides will be focused on my experience on the regulatory process in both China and Canada. In China, the regulatory framework has several layers. on the top is nuclear safety law, and then under that, it's the nuclear safety regulations, which they call HAS. It's issued by the state council or the ministry. And then under that, it's the nuclear safety guides, which they call HAD. It's issued by the ministry. And then there's a mandatory national standards, and there's also recommended national standards. So the regulatory body in China is the Ministry of Ecology and Environment. And within this ministry, there's a National Nuclear Safety Administration, which is solely responsible for to regulate the nuclear part. But the environment impact assessment is done by the Ministry of Ecology and Environment. So the process, it has been a major update of the process in October 2019. So I'm talking about the process after that. There's several steps here. First of all, you have to get a license for site. The site needs to have a safety analysis report and environment impact assessment. And after you get the site license, you need to apply for the construction license, which of course requires the preliminary safety analysis report, the PSAR, again, the environment impact assessment, the quality assurance plan, and other supporting documents. The license to construct is valid for 10 years. And then after that, you have to apply for the license for initial fuel loading. It's for the commissioning of the reactor. You need a final safety analysis report, QA, emergency response plan, and other things. And once you get this license, you can load the fuel. You can reach the initial criticality, and then you have to do tests. And once you meet all the requirements in the license, once you've done all the tests, and once the regulator review it and happy with it, you can apply for the license for operation. So that's the formal operation. And by that time, you need to have a maintenance plan, in-service inspection plan, reviewing plan, pre-service inspection report, and also initial fuel loading report. And this license will be valid for the design lifetime. So if your design lifetime is 30 years, the license will be 30 years. If it's 80 years, and the license will be 80 years. Then of course you have to, once you try to decommissioning the facility, you will have another license. And also the regulator in China offer optional process or service. For example, they offer a concept called combined license permit. So you can combine those licenses. You don't have to go step by step. If you have confidence in your design, and more importantly, if the regulator has the confidence in you, and you can apply for the combined license. For example, if the regulation actually stated clearly if the concept is factory assembled floating plant, you can apply for a combined license. And also the encourage pre-license engagement. There's a variety of forms of doing that. There's no formal process to guide that, but the engagement is also is always encouraged. So in Canada, I spent the last 2.5 years in Canada working with the CNSC. So in Canada, on top, there's an act passed by the Parliament. For example, the Nuclear Safety and Control Act, which we call NSCA. And then under that, there's regulations. The regulations made by the Canadian Nuclear Safety Commission, CNSC, authorized and approved by the governor in council, but it's mainly just CNSC making those regulations. And under the regulations, there's licenses and certificates issued by the CNSC. So the applicant is bounded by the license, and often the application is supported by SAR, by Safe NAS report, and the Safe NAS report is part of the license. So the applicant is required to follow what they said in the Safe NAS report. And then CNSC also have this regulatory documents, which they call RegDoc. And these documents basically give you the detailed guidance on what you need to be doing. The regulatory body, in Canada, CNSC is the independent sole regulatory body for nuclear in Canada. And not only nuclear power, but also nuclear medicine, laboratory activities, anything that has anything nuclear will be under CNSC. And however, after 2019, there's a new act passed by the Parliament. It's called Impact Assessment Act. So basically, it expands the requirements of the environmental impact assessment. Now, not only the impact to the environment will be assessed, the impact to the social economy will also be assessed. So that is managed by an independent impact assessment agency. So let me just go to the next slides. And so again, the licensing process I'm describing here is after August 2019. So it seems that in 2019, both China and Canada updated their regulations. I believe there is also a major effort in Indonesia to ramp up the regulations during that time as well. So in Canada, you have to apply for the license to prepare site, and there's a required minimal time to be given to the CNSC to review the application. And also after that, you have to apply for the license to construct. Then there's a license to operate. There's no commissioning license or fuel loading license, but just right to the license to operate. And then you have a license to decommission. But if the project is big enough, it has to go through the impact assessment before any license can be issued. The CNSC actually offer optional process or services. For example, as Canada is also offering the combined license, which is written in the regulation. So you have choice to combine the license to construct and license to operate, which will reduce the minimal time to 40 months. If you do it separately, it would at least take you 56 months. But if you do a combined license application, it's reduced to 40 months. But whether you will be qualified for that, you have to negotiate this with the CNSC. CNSC also offer a formal pre-license engagement, which they call the vendor design review, VDR. And I was doing that effort with CNSC in Canada. And they also offer a 4-step process to determine the license strategy. And this especially applicable to new technology. Basically, the idea is for the regulator to get familiar with technology to develop a strategy to license the technology. Okay, so I guess that's all the slides I had. I put all these references here. So if you have any if you want to know more details about the things I'm talking about, you can definitely check those references. And also, I'll be happy to answer all the questions you have. Thank you very much.
Thank you, Kun. All right, I think now it's the time for question and answer and discussion. I'll open up the floor for everybody to ask question. Go ahead, just speak up. Anybody? Pak Tagor or Pak Hedi, please help, conducting the question and answer period session.
Bob, do you know how do I stop sharing this?
Oh yeah, you click on the top, on the very top. If you look at the very top, very top, and you see stop share. You go to the top.
I don't see stop share.
At the bottom.
You can
find
okay,
good.
Okay.
All right. Thank you.
All right. So
I have several questions. Maybe because I want.
Pak Siddiq, silakan, please.
Yeah. Thank you, Dr. Kun, as inspiring presentation. So you mentioned about the history up to the deployment strategy in USA, but it's already decided to not. They decide to choose the other technology, like water reactor technology, as well as in the uranium fuel cycle. So in terms of sodium fluoride, and in this stage, many MSR developer choose the other side, like chloride, and also combined with lithium. In terms of the stage of corrosion, how about the stage of because the objective of one of the objective of this molten salt is to hardening the spectrum to have much more converter reactor, converter fuel. In terms of this subject, is there any typical reason change from the sodium to the chloride and so on? That's my first question. And the second one about the as far as I know, Russia also developing the molten salt program. Usually they use Mozart and bring together the transuranium. They burn the transuranium fuel. There's another purpose for this reactors. So in terms of this application, they try to make the transition from the as you may know, they have long history for the liquid metal technology from the lead, bismuth, and so on, and then turn to the molten salt coolant and also the fuel. As per your investigation in comparing to Russian technology. And the third one about the grouping or classified technology based on the molten fuel itself, and then the moderator, and then the some part of the fuel. But if we take a look at the other side, the other classification is also based on the solid fuel, but the coolant or the primary or the secondary is also by salt moderator or salt coolant. So not the fuel become the molten itself. They just use the molten as the fuel, not fuel, with fuel, but for the coolant only. And because the other application for the molten, because they are very good heat transfer and heat capacity for this salt, in some energy developer, they use also for the energy storage, let's say for the concentrate PV photovoltaic, thermal photovoltaic, thermal power plant. In that sense, do you have any experience or maybe I'll say the comparison between this mix salt in comparing to high capability to for storage or heat transfer capability for those chloride and natrium. Okay, thank you, Professor Kun and Pak Bu.
Thank you.
Okay, thank you very much for your question. Let me try to summarize your three questions and make sure I understood them correctly. So the first question about using sodium chloride as a salt. You're asking the corrosion issue and perhaps other issues associated with using sodium compared to the use of lithium. And the second question, I believe, was about the Russian development of MSR, using Mozart, using MSR to burn the nuclear waste, and their relationship of their molten salt and with their lead-cooled or sodium-cooled fast react technology. Then the third one, if I understood it correctly, it's about first of all, it's about the molten salt cooled reactor and the heat storage using molten salt. Okay, so if I understood them correctly, let me try start with the first question. Regarding using sodium, so the lithium fluoride salt has the benefit of as a moderator, because lithium, the element of lithium is much lighter, and so it has much better moderation compared to sodium. So, and the reason that you can see there's several vendors, several companies, and also national labs, they're not using lithium, including Oak Ridge itself. They're exploring other salts. It's because it's hard to get lithium, enriched lithium-7, and lithium has natural isotope ratio of I think 10% or 20, I don't remember exactly, but you have a quite large amount of lithium-6, which under neutron irradiation, you will generate tritium. So you have to enrich lithium to have a 99.9 above lithium-7. And that enrichment proved to be difficult nowadays. The only viable way of doing that is currently viable. Maybe there's new technology, but currently there's only a mercury method that is available. And most of the countries, including the US, Europe, China, Japan, they all banned using mercury technology. And Russia is the only country that still have a large facility that can use mercury method to enrich lithium-7. Even for that, they only have like several tons of lithium-7 in storage. I don't know their capability, but not very much. And considering we're thinking about deploying molten salt reactor in the large scale, and that lithium-7 capability is not enough. So that's why people switching to other salt. Now, by switching to sodium, you resolve you don't have the supply issue, but it will provide less moderation compared to lithium. So that means you have a less ideal neutron performance. For example, you will have a less efficiency on fuel use, on fissile material use. You will have a less, how do I say that, less negative reactivity coefficient. So all those kind of things. But in terms of corrosion control, sodium and lithium are almost the same. And for any sort, any structural material, even if you use nickel, you still have to control the chemistry of the sort. The oxygen level has to be kept under, say, maybe a few hundred ppm at most, in order for your component to last long enough. It will be the requirements. If you use stainless steel, the requirements on the sort chemistry control will be stringent compared to nickel. But nickel still require chemistry control. Stainless steel still require chemistry control. Everything requires chemistry control. It just nickel will be corrode slower compared to stainless steel. So if you use stainless steel as structural material, you could either make the vessel wall thicker, or you could reduce your operating time. Say you replace your components from time to time. So there's a way to resolve that. So that's my answer to the first question. And second one about Russia. And so the Russia effort was mainly in Kurchatov Institute, KI. Their scientists, engineers participate the IAEA and Generation 4 forum every year. So their MSR concept is supposed to be a waste burner. So you just throw the waste into the molten salt reactor, and hopefully you burn it. You burn down the actinides. And the concept, if you just consider the reactor concept, it's a good idea, but it requires reprocessing of the used fuel, which the technology it's not mature enough. So you may hear a concept saying, I don't need any reprocessing to burn used fuel, which is not true. If you do the neutronics calculation, you will find that the idea is well, you will need reprocessing, and some people choose to use another name. They don't call it reprocessing, they call it purification, they call it separation, they call it exchange, but you have to separate the element, whatever you want to call that. You have to have a chemical process associated with your molten salt reactor to have a meaningful burning of actinides. So that's that might be just my personal opinion, but you can always do the neutronic study and to figure this out. The third question about energy storage. Yes, so the molten salt cooled reactor, they're just using molten salt as a coolant. They don't use it as a fuel. The idea was originally from Oak Ridge and University of California, Berkeley. They're using trisul fuel, which is common fuel used in gas-cooled reactor. They just replaced the helium coolant with the molten salt coolant in the hope to increase the thermal efficiency. And whether you could use salt as energy storage means, I think you could. The uncertainty is about the economics. So if you look at this salt heat storage idea, that was originally from the concentrated solar power, right? You want to look at those concentrated solar power plant and to see how they're doing with their sort. And if they're doing okay, you probably just want to borrow their technology. And if they're not doing okay, you need to think about how to optimize that. But in the nuclear industry, I haven't seen people successfully doing energy storage. And there's also other ways of doing energy storage. Like people are also thinking about using fire rigs, and several ideas were proposed by MIT and Oak Ridge in the past. But that's a area. Well, actually, you know, one of the Moltex, I was working for Moltex. One of the Moltex idea was to use a sort as heat storage means, but that was never commercialized.
Thank you, Mr.
I hope I answered most of your questions. But
yeah, thank you very much.
Okay, any other questions, please?
Yes, Pablo.
Okay, yes, Professor.
Pak Ferry Wibisono.
Oh, yes, please, Pak Ferry. Go ahead.
Okay, thank you. First of all, thank you, Professor Kun Chen, for a very good and very informative presentation. You mentioned in your presentation about this technical issue that they found with the MSRE experiment. And then basically you said that most of the issue was actually been resolved in the 1970s. And I know that you've been working for several years with molten salt reactor. I think what I'm curious to know is, like, in your view, what is the main challenges? What is the main technical challenges for MSR development today? I mean, is it finding the best salt composition, or is it finding the best reactor configuration? You mentioned before about this graphite-based MSR, homogeneous, heterogeneous, or is it understanding how material behave under salt irradiation? Or is it like what you mentioned just now, like how to integrate the reprocessing to the MSR itself? So I'm just curious, like, in your view, what is the main technical challenges, and basically how Thorcon plan to tackle those challenges in the future? And the second question, I think it's probably because of my understanding of license procedure. Like you mentioned before in your last slides about comparing the licensing process in China and Canada. So I think my question is just in general, like, who has the authority to decide like how the licensing procedure should be? Is it the regulatory body in the country itself? And for a country like us, like Indonesia, we never have a commercial reactor before. Like how we need to set up this, like, is Bapeten has already guidance on like how the licensing procedure will be, or will IAEA step in and basically help us in deciding what we need to do to kind of like obtain the license if we really want to pursue this MSR development? Thank you. That's my question.
Thank you very much, Professor Ferry, for your questions. So your first question is about what are the main challenges for developing and deploying molten salt technologies. The second one, I guess, about the comparison. It's about who has authority in China and Canada to make the decision to license a new technology. So first, the first question, if you think about what are the biggest challenges for deploying a nuclear technology, I can try to give you a general answer. For any nuclear technology, the biggest challenge is always material. So the technical challenge is always with material. For molten salt, so if you think about the material, the biggest challenge is the structural material. The people have been trying using nickel alloy, and both the nickel alloy and stainless steel. The challenge for the nickel alloy is that it's expensive to make, and also it's relatively difficult to manufacture. So the WASH 1222 report identified the neutron embrittlement of the nickel alloy, which was kind of mitigated by changing the composition of the alloy back in the 1970s. The issue right now is really the manufacturing, the cost, and also the challenges to manufacture the components and weld the components. The stainless steel, as I mentioned, is much easier to make and much cheaper to make. It has less resistance to corrosion under the same circumstances compared to the nickel alloy, but it have a superior features on other categories, and most importantly, it's cheap and it's easy to make. But the concern, except for the neutron irradiation, there's also another concern on corrosion. In order to control the corrosion, we have to control the chemistry of the sort, regardless of what alloy, what material you're using. And that may be challenging because people have only done things in the small scale. In the laboratory, they do chemistry control, they do corrosion control, but in the large scale, they haven't done that. It's much harder to do it in the large scale. So corrosion and also the neutron embrittlement are the challenges, but they're considered to be manageable. It just people don't have the experience. We haven't built any molten salt reactor for many decades, since the 1960s. There's a lot of new technologies that we can use, but that hasn't been tested. People have to be given the opportunity, or people have to be allowed to test those ideas. And I have the confidence that those issues can be resolved, but I don't have the evidence. So if I have to talk to the regulators and they ask for the data, I don't have all the data. If we can have some test bed, we can have some test facility, that would be very helpful. Regarding the sort, the lithium-7, I think it's only challenging on making the sort. The rest of the challenges are actually, again, it's the production, the mass production of high quality sort. Again, it's relatively easier to make several kilos of high quality sort, but in terms of the hundreds of tons or 1,000 of tons, the current sort industry, they make very cheap sort. They low quality cheap sort for other purpose. They don't make things for us. So they have to improve their chemical process to produce high quality sort in hundreds of thousands of tons. And then for all the MSRs that are using graphite for moderator, you have to have a supplier who can produce a high quality graphite for you, which is slightly different from the ones used in gas-cooled reactor. The gas-cooled reactor graphite can have a relatively larger pores, and they can be porous, but in the molten salt application, you have to have those fine graphite that don't allow the salt to penetrate into the graphite too much. There was actually a solution for that. The Chinese TMSR project was able to buy those kind of graphite from several suppliers in China, but they're still making it in small quantity at this time. There needs to be investment to expand their production capabilities. So in general, I think in terms of material, we have this solution in the laboratory scale. We have to have an opportunity to expand that scale and to do a test to demonstrate that they can be done in a large scale. I think those are the major challenges. And there's other challenges like high temperature. In high temperature, you have the need to have a special instrument, special operation procedures, special components, but those can all be resolved. So based on my experience in SINAP, those can all be resolved. So that was for the first question. The second question about who has the authority. Yeah.
Sorry, time out. You forgot to answer his question regarding how does Thorcon address those challenges? How does Thorcon address those challenges?
Okay. So in terms of material, Thorcon is using stainless steel, which will avoid the treatment of nickel alloy. It will not get into the business of making expensive alloy, nickel alloy. So in that sense, stainless steel is good candidate. And so what Thorcon will have to do is to control the chemistry of the source to mitigate the corrosion. But the advantage of the Thorcon design is only have 4 years to 8 years lifetime. So we always replace the components. So that basically mitigate the corrosion issue. In terms of a sort, so we are using sodium instead of lithium, so we don't have the lithium headache. So all we have to do is to find suppliers, to help the supplier to ramp up their capability of making those salt. And we have actually found those suppliers, and we can just buy salt from them. And the only thing Thorcon needs to do is to make sure that we do extensive tests and make sure the suppliers are following the quality procedures, and when they develop 100 tons of salt, the quality is the same as they said. That's basically a quality control issue. For the graphite, again, the challenges are there, but the benefit of Thorcon design again is we're only going to use it for 4 years. So the replacement time was actually determined by the lifetime of the graphite. So the basic Thorcon concept is that we don't try to prove a component can last for 80 years because it's hard. Without really let it run for 80 years, how do you know? You can do accelerated tests, but there's always argument that there will be some phenomenon you don't know 80 years from now. So our strategy is actually replace the components. We only operate for 4 years. The 4 years is the time that MSRE has operated. So it's within our knowledge boundary. So that's a strategy. I think it's going to be working. Okay. So that was for the question about the main challenges, and for the question about the authority. So Professor Ferry, there's two type of answers. You can always go to the paper and say that who has authority, but there's also a reality. So in reality, in China, the government decide what project they want to do, and the regulatory body will support the government decision, whatever that is. And the regulatory body is just try their best to make it safe, to make the project safe. So again, whether it's gonna be AP1000 or EPR or Chinese Hualong or VVER, it's all the government decision. And that's a much better independence. So basically, CNSC can kill the project if they're not happy with the safety. However, having said that, the government of Canada also had the influence on CNSC. For example, the government can say the SMR, the small modular development, is the priority for Canada. And if CNSC is saying, I don't have the resources, I don't have the capabilities, and then the government of Canada will say, develop those capabilities, obtain those resources. I want you to regulate SMR. You have to be able to do that. So again, in both cases, the government has the influence on the regulators. It's just how much the influence the government can have.
Kun, a follow-up question. Actually, Professor Ferry has a point about the IAEA. So in your opinion, I'm just following it up, that in a country where, for example, like Indonesia, which hasn't have any nuclear power plant, where do you think IAEA fits in the big picture? Where are they, in your opinion, are they leading the way, or are they guiding, or where do you think they fit in the big picture? So, because I mean, that question actually has been lingering in the government mind. So, okay, please answer that question.
Yeah, sure. In my opinion, I think IAEA can be the advisor to the Indonesian regulatory body or government. I don't think IAEA has the capability of leading the effort. The IAEA is composed of experts from all the member states. They have a term in IAEA several years, and they come and go. And IAEA is also now known for its efficiency and determination. So if you look at all the countries that had successfully developed nuclear technology, and they all have their own strong government support and regulatory agency to do their domestic regulation. I mean, there's examples that some countries rely on the IAEA, but if you look at those countries, those are relatively smaller country with less population and with less demand of energy. In those examples, it probably won't make economic sense for them to establish their competent regulatory agent because they're so small. But in larger countries with big market, it's always good that the country has its own strong regulatory body and taking the lead and doing the work. And IAEA can be a good advisor, but if you rely on IAEA, I don't know how long it's going to take them to actually realize the goal you want to achieve.
Okay, so the Indonesian regulator should be leading the way, not the IAEA.
Correct.
Okay. Right.
I have a question, Pak Bo.
Please, Pak Waris, go ahead.
Okay, thank you very much. Thanks very much for Professor Kun Chen for very comprehensive explanation about the story or history of molten salt reactor. What's the problem, especially in molten salt type like sodium fluoride and lithium fluoride, and also about the structure. But I have a small question about safety. I think you didn't mention about the safety aspect of MSR compared to other generation of technology, especially you just mentioned about the passive heat removal. But can you explain in more detail about that? Thank you very much.
Yeah, sure. Thank you very much, Professor Waris, for your question. So I can give you a short introduction here. There will be a detailed introduction in the following weeks on how those systems are working. So basically, the focus of the passive decay heat removal system is to remove the decay heat without using any external power. So the design as it is, it's actually having several steps. So first of all, let's say if you lose all the power, if you don't have any AC power or external power, then obviously when you lose the power, your shutdown rod will drop, which is a common feature for the shutdown rod. So the fission will stop within a very short period of time. And then the majority of the heat in the long term will be from the decay heat of the fuel. In that sense, because you lose all this power, you don't have all the circulation, you don't have the heat sink, and the temperature of the salt will increase. And at the bottom of the core, which we call the port, there's a freeze valve, the same as the one that's very similar to what MSRE was using. So when the temperature increase, when you lose the power, the freeze valve will melt and the salt will be drained to what we call the fuel drain tank. And that process is gonna happen within 10 minutes. So it's very short period of time. And once the salt is getting to the fuel drain tank, it will stay there. So the focus now is to how do you cool the salt and the fuel drain tank after those 10 minutes. What we have is what we call cold wall. It's basically a double steel wall. The wall is in between the double steel wall, there's water filled. And then the heat from the fuel salt will be transferred by radiation, by conduction, and maybe convection a little bit, but not much. The heat will be radiated to the cold wall, and the water will be heated, and the water will flow because of the expansion of the hot water, and it will flow in the wall and to a cooling pool, and then will be cooled in the cooling pool, and the water will flow back to the cold wall. So a water natural circulation will be established in the cold wall. But the question is, okay, how can you cool the water in the, how can you cool the natural circulation loop? We have a cooling pool, which has a lot of water, and we done the calculation, and we think the result of the analysis show that that pool can last for 145 days. So you have that period of time, you don't need any intervention from the outside world, and that can last for 145 days. But what about if you lose that pool? We have another way of doing that. Doing the heat transfer, the whole power module, which basically reactor, is submerged in the water-filled basement. So everything is water-filled, and even if you don't have this natural circulation, just by heating the surrounding water, this fuel can be cooled for over 200 days. So by that time, the decay heat will be low enough. You don't actually need any additional intervention. So the whole idea of the Thorcon plant is not to require any external power, actually any power to remove the decay heat. And it was possible because the salt has a very high boiling point, and also because we're using stainless steel, it has a high operating temperature, so we can tolerate a rise of temperature. And also with all this water, with all this natural circulation design, we can do this without any external power and intervention. But I will show you the system, and we'll show you how it works in the following weeks.
Thank you very much.
Thank you, Kun. So there's a question on the chat room. I need to read it because from Professor Alexander Agung, he said that his internet connection is not stable, so he write it up. He said, "Thank you, Professor Chen Kun, for your interesting presentation. You mentioned that the lifetime of the reactor is 4 to 8 years, if I'm not mistaken. So do you think that this short lifetime will create more irradiated material as alloy, graphite, etc. as waste as compared to long life reactor? And how Thorcon will overcome this?" That's the question.
Yes. Thank you very much for this question. Definitely yes. So what's happening is the plant itself has a 80 years lifetime. What's being replaced is the core. So reactor core, or we call the power module, will be replaced every 4 years. So 4 years operation, 4 years cooling. Then after 8 years, the core will be removed, will be replaced by a new core. We actually generated by doing this. Yes, it will be more than if we don't replace the core, but the volume are still very small. I think we have done a analysis on the volume of the waste, the total volume of waste after 80 years operation for each of the Thorcon power plant, and those volumes are still very small. So it's really about a balance, whether you could accept a slightly increase of the volume of the waste to gain the benefit of the safety and economy of the power plant. In terms of how do we handle those waste, so basically the core contains stainless steel structure and also the graphite. And the stainless structure, which if some parts in contact with the salt, it needs to be flashed again by the salt to remove the residue used fuel. If it's not in contact with salt, then it will be handled the same as other power plants. The graphite itself, actually, I think if we consider the waste management, it will be the major issue. And we do have some concept of how do we handle the graphite. I think I will be able to share with you more details on those issues, maybe in the coming weeks. Yeah. Bob, you're muted.
Right, it's coming to 9:51. I would like to ask the participant whether we go to just 10 o'clock or we want to go to beyond 10 o'clock. So if we go to 10 o'clock means that maybe one more question or two more questions. So let's stop at 10 o'clock. So maybe two more questions, please.
Sir Bob?
Yes, siapa? Oh ya, Pak Hendra.
Pak Hendra.
Ya, silakan Pak Hendra, please.
Good morning, Mr. Kun Chen. I have a question regarding design criteria that Thorcon have, and SINAP design is almost same, the feature. I wonder that what are technical requirements used by NNSA to grant construction permit to the SINAP? And then do they have any specific design requirement for MSR? And my second question is how much the enrichment for uranium-235 and thorium-232 in the Thorcon design? Thank you.
Okay, so two questions. First, question about the licensing of the SINAP TMSR LF1. So what type of special requirements the NNSA had put on the SINAP? And the second question, the second question was about. Sorry, can you repeat the question?
The enrichment for uranium.
Oh, okay.
Okay, and
Yeah.
thorium. Yes.
Okay. All right. So first question, so what happened with NNSA is that when we started the licensing process, there was general requirements on radiation protection, on quality assurance, on those things, but there was no special requirements for a molten salt. As you can imagine, there was no molten salt reactor was licensed in China in the past. So what they did was that SINAP had to submit their design requirements or design criteria to the NNSA first. And the NNSA reviewed the design requirements and make sure the requirements are meeting the NNSA's regulatory requirements. Of course, there's a back and forth discussion between SINAP and NNSA, but finally, the NNSA agreed that if the design follows the requirements, it will also meet the regulatory requirements from the NNSA. So basically, it was not NNSA issued any special requirements to SINAP. It was actually NNSA asked SINAP to come up with a set of requirements, and they review it. They don't call it approve because there's no formal approval process. They call it agree on that. And as you can imagine, the reason why they do that is because as a new technology, SINAP might in a better position to do that compared to the NNSA itself. And then after that, NNSA did one thing. So they summarized their discussion and design requirements with the SINAP, and they came up with a review guide for their reviewers. But even for that, SINAP and myself contribute a lot to the guidance of the review, again, because we were much familiar with the technology. So NNSA was able to use the applicant as a resource to develop those requirements and guidance for them, and they review it, they agree on it, and through that discussion, they also gain knowledge on the technology. So that's what really happened with NNSA. So for the second question, Thorcon currently, the enrichment of uranium-235 in the field is 19.75%. There's an ongoing analysis. We have another alternative which have a lower enrichment level. And the reason we have a backup enrichment is because we know buying 19.75% enriched uranium could be a political challenge for some of the countries. And thorium is natural thorium. Natural thorium means a natural isotope ratio, but the thorium salt will be high purity.
Okay, thank you. Very interesting answer. Thank you, Mr. Kun Chen. Prof Kun Chen.
Thank you.
Pak Bob, I think there is a question, one question from Azizul Hakim.
Makasih, Pak Bob.
Azizul, please. This is the last question, I think.
Thank you, Pak Thakur. Thank you, Mr. Kun Chen. And as you mentioned that there are actually several differences between MSRE and Thorcon MSR, such as you don't use nickel base alloy anymore. The fuel are also different, and the graphite log or graphite geometry you're using for the moderator is also different. But Thorcon design is the scale up of MSRE. So in what sense that you claim the Thorcon MSR is the scale up of MSRE? That's the first question. My second question is that you mentioned that there is an issue on radiation data and dimensional change on the graphite of MSRE due to high fast neutron fluences. One of my students calculated and compared the high fast neutron fluences between MSRE and Thorcon MSR, and confirmed that Thorcon MSR operating at 4 years will have higher neutron fluence, and that means that you may expect that there could be dimensional change in your graphite moderator. What do you anticipate in terms of flow differences, flow changes in the core, and even neutronic performance in the core when the dimensional change of graphite happens? Thank you.
Okay, thank you very much for the question. So let me try to answer this briefly. Let's do the second question first. So how do we, so what are the, I guess the question was really about what are the criteria for Thorcon to follow in terms of using graphite. As we know that when irradiated by fast neutrons, the graphite will first expand and then shrink. So those kind of changing directions make it very challenging to handle. So our idea is that we make sure during the lifetime of Thorcon core, which is 4 years, the graphite will only change its dimension to one direction, which means it only expand. We will not reach the point that the graphite start to shrink. So as long as we make sure it's changing to one direction, we can manage that. And so that is our principle. So that means it's okay if we go above the radiation fluence, the neutron fluence of the MSRE, because we must go above that. We're a 500 megawatt TARP run. They only have like 7 to 8 megawatts. So we'll be definitely above that. But as long as we're in the expanding side, we're not on the shrinking side, we'll be fine, because there's other people have done graphite study, like the high temperature gas graphite people. They have irradiated graphite for very high neutron fluence. So we can use that data to support our design. In terms of the first question, why we say it's a scale up. It's really about the it might be easier for me to explain it if we, in the next week's presentation, when you say the structure of the reactor, you will find that it's very similar to MSR. The flow chart, if you draw a flow chart, it will be very similar. But there's a replacement of elements in that structure. For example, the structural material. For example, the replacement of lithium-7 salt with sodium. So there's several elements that have been changed for a good reason, but the overall structure are very similar. I think it'd be much easier to explain that in next week's presentation when you see the overall picture of the Thorcon. I hope that at least partially answered your question.
Thank you.
Thank you, Dr. Kun. How about now, Pak Bob? We will close or?
Yeah, I think it's 10 o'clock already. So if we don't have any other questions, I think we close the session for tonight. We still have another 5 more weeks to go, so more questions to go. So with that, before we close, Kun, would you like to give a last statement to the participant before we close the session?
Yeah, sure. Again, I want to say it's my honor to be here and to be able to share my experience and yours, to learn your thinking on MSR. I'm very much look forward to the coming weeks. I'm hoping we can have this discussion all the weeks again, but it's I don't know if it's fortunately or unfortunately we have to have this meeting over Zooms. I'm always looking forward to visit the beautiful country of Indonesia. So I'm going to get my second dose of vaccine this afternoon. So hopefully I'll be able to visit you in the future.
Yes, very good. So with that, I'd like to say thank you to all the participants. I think Pak Tagor has shared the Professor Kun presentation on the WhatsApp group. And for next week, if everybody have specific question or specific issue that would like to be addressed by Professor Kun, please share it with Pak Tagor so he can put it in the presentation. Thank you very much, everybody. So thank you for the participation. Good. Thank you very much.
Thank you
very much.
Bye-bye
now.
Thank you.
Yeah.
Thank you very much, Profesor Kun.
Yeah.
Terima kasih, Dr. Kun.
Yeah.
Terima kasih Pak Bob.
Terima kasih.
Terima kasih
Tagor,
semuanya.
terima kasih Bapak Ibu
Thank you
semuanya.
semuanya. Izin.
Terima kasih Pak.